So, this is a lecture on the section of 6.2 regarding the phenomenology of transmission and reflection in our course in optics. And what I will do in this lecture is that I will introduce to you some basic terminology to describe and understand processes of reflection and refraction. So I will introduce to you the laws of reflection and refraction, and that would be more known as the Snell's law. And I will revisit at the end, or towards the end, the concepts of optical path length and introduce to you the Fermat's principle that can be also used to understand what happens when light is being refracted at an interface. So this is what I will be speaking during the lecture, and I want to start here briefly by just trying my best to elucidate to you that here in our treatment we are really looking on our processes and what happens for the light matter interaction on a macroscopic scale. So we have refractive index n that tells us the speed of light inside a given medium, and this is of course a macroscopic parameter, and thus our treatment is purely macroscopic. And this is really most of the time the main parameter and the only parameter we need to know in order to understand what happens for propagation of light. So refractive index is really an important parameter, and it's a macroscopic parameter, and that's it. And in here, what follows, I think it's good to keep in mind that this concept of refractive index, it's really a macroscopic quantity, and we do not have such quantities, for example, in the microscopic formulation of Maxwell's equations, where we in fact do not have any refractive indices at all. There's no media. There's just individual electrons, charged particles that give rise to electromagnetic radiation. So it's rather this complex interaction with light, with many electrons and atoms that then gives rise to these macroscopic quantities. And this is what I try to say. So there are many different levels that we can try to understand what happens. And then of course, in all of these processes, in reflection and refraction, those would be the main processes of interest here in this chapter. Always what happens is that there will be this atomic scale or microscopic scale of light matter interaction. And this microscopic light matter interaction is really better described using a concept of dipole moment, small p, which is defined that it's the vacuum permittivity epsilon naught times polarizability of my particle, atom, system, electron, emitter, scatterer, times the incident field. And this would be the local field that this particle, object, atom, building block that the matter is formed out of, what is the field nearby this building block. So this is really the local field that is filled by the particle, described by the polarizability. And this is what I mean a microscopic light matter interaction. What happens, for example, with a single atom in my bulk medium. And here in this chapter and in the follow-up chapters, we're really more interested on the macroscopic scale of things and on the macroscopic light matter interaction. And this interaction is better described with the equation where we have capital P. So this is our material polarization, which is defined that it's the vacuum permittivity epsilon naught times chi. This is the material susceptibility times the incident field. And this is the incident field on a macroscopic scale. And here, the key thing here is the chi, the material susceptibility. And this guy here essentially tells us that what will be the refractive index profile of my material. And this is the main quantity of interest. And once we know that, we can use the macroscopic Maxwell's equations, and then we can actually do all that we will be doing in this chapter. So here, we are again, we end up with the concept of refractive index of the medium. And this is the key parameter we need to describe things right now. So now let's get started. Now that we know the subtlety involved, let's start by considering an interface between two homogeneous medium, and homogeneous medium so that we do not need to worry about scattering, but rather just all this reflection and refraction happens quite cleanly and neatly. So this is what we must assume out of the medium and their interface. So and the medium interface is quite smooth. We can even assume that it's atomically smooth, or at least smooth with respect to the order of the wavelength of incident radiation, so that the surface smoothness doesn't do much to disturb the reflection / refraction of light. And these two media, let's denote them with two indices, so I and T, and the kind of plane of interest for us is so-called plane of incidence, and this incidence plane is the plane that is being defined, that it includes the vectors of the incident ray, so that the incident plane wave incident on this interface Ki, then we have the wave vector of the reflected wave Kr, and then we have the surface normal of our interface. So this is the picture that describes what happens in our system. So we have the incident plane wave coming in here, defined. The direction of this incident plane wave is defined with the wave vector of Ki. Then it is being reflected, and then the reflected plane wave, the direction of which is being described with the wave vector of Kr. And here we have the incidence angle theta I, and we define that with respect to the surface normal n hat here. And please note, if you remember, for example, if you're more familiar with electrons being or Röntgen rays being scattering like a Bragg reflection, then please be warned that in different concepts and contents, this angle of incidence is being defined differently. So in optics, we define it with respect to the surface normal, but especially when we would be shining electrons in here and would be looking how the electrons are scattering from a periodic structure, we would be defining the angle of incidence with respect to the plane of the interface. So please be warned that in other occasions, the plane of incidence, not plane of incidence, but the angle of incidence might have a different meaning, different definition. So what we do here is that we assume that the refractive index of the medium from which light is incident is denoted with Ni, and the incidence angle is denoted with theta I. So these are the kind of definitions we assume for the material that is from which the light is entering the interface, and then the lower medium, like the material lower on the figure, we label that with the index T. So then the refractive index profile of that material will be NT and so forth. And if these two materials are, let's say, optically different, so that the optical density is different, and with optical density I essentially mean that the refractive indices are different. So if Ni is not NT, then what happens is that part of the incident light is actually being reflected. So this is what happens when the two materials look different from the optical point of view. And let's be clear, of course, their density the actual density might be the same, and the mass might be similar. But here we speak of changes or differences in the refractive index profiles. That's the only thing we need right now. The angle theta I, this is the angle between the incident rays, wave vector Ki, and the surface normal, and please note that this is the way how we define the angle of incidence in optics. And now let's try to understand things by looking at the wavefronts. So we can consider how a wavefront of AB, defined in the figure with a slightly more bolded red line, let's see how that propagates this one specific wavefront. And the different parts of the front that encounter the interface, the line AD essentially there, is being encountered at different times. So this wavefront is being propagating into the interface, and the interface is essentially the line from A to D, and that at the different times the light is being reflected. And this is what happens conceptually here. For the CD wavefront phase, that would be the phase bolded in blue for the reflected wave. We require that the phase of this wavefront will be equal to the incident wavefront. So that that the other way of saying is that the optical path lengths of AC and BD must be equal. So that we require the wavefronts to be identical, not identical, but equal. And then what this means that then the lengths of from this point A to point C must be the same as from point B to point D. And when this applies, of course, from the figure, we can extract a few equalities so that the length BD, the line between the points B and D, essentially it's the AD times sine of theta I, the incidence angle. And similarly, the line length of from point A to point C is equal to AD times sine of theta R, where R is the reflection angle. So this is basically just looking at the figure, and together these result in a condition that AC, the length of AC must be the same as BD. And this essentially gives us the law of reflection, so that the theta I is equal to theta R. Sorry, I think I said it in a silly way. So essentially, these two equations, like we can look from the figure. And if we require that AC equals BD, the lengths are the same. So essentially, this is what we do require, like these lengths should be the same. So that means that then these angles must be the same, because otherwise the equality would not hold. So essentially, it's this condition that gives us the law of reflection. And now we have solved everything there is to know regarding reflection. So let's now schematically look what happens for the transmitted light. So let's now consider the propagation of ray front AB and towards into the material T. So this is now what happens when light is being transmitted, and essentially, of course, light is being refracted due to the fact that the phase velocities are slightly different. So that the speed of light for the light is different in the upper material I, than in the material denoted with the label T. And now for the phase of the wavefront ED, so that would be equal to the wavefront of the incident wave, essentially the optical paths BD and the AE should be equal. Now again, from the figure, we can derive two equalities, so that the BD, length of BD line times NI is equal to AI times NT. So let's look at this, so that the BD here is this line here, B coming from D, and the ray is propagating in material I. So of course we should multiply the length with the NI refractive index, and here AE is essentially this here. And if we require that the phase of the incident wave would be the same here in these points E and D, that then implies that the AE times NT must be equal to this. And similarly, we can write that the AE should be equal to AD times sine of theta T. So let's look at here. So AE would be this line here. And then from geometry, we see that this is the hypotenuse, AD times sine of theta. We should get the same line here. So from figure, we get these two equalities, and now we can use to derive the law of refraction based on these. So essentially, we can equate that the NI times sine of theta I must be equal to NT times sine of theta T. And this is known as the Snell's law. So essentially, this is what it boils down to. So we are just basically plugging this into here, and then we are plugging in something similar into here, and this is from where we get things. So nothing strange here in a way. And now we have, in a way, at least maybe not derived, but at least motivated the Snell's law. Like in the follow-up chapter, I will actually derive the Snell's law, or what I would be more happy of saying deriving, because I'm then using really Maxwell's equations to verify that this actually does work like this. Now, here what happens basically in these pictures and our treatment, we have implicitly assumed that the medium T is optically denser, and that of course just means that the refractive index of NT is larger than NI. And what this means is that then the rays tend to bend towards the surface normal. So theta I is larger than theta T. So in case you're not familiar from high school physics about the kind of basics of refraction, please memorize this rule of thumb and this picture. It's highly useful in the future. So for example, in terms of practical examples where this happens, we could, for example, consider a normal air glass interface, and there the light rays would be bent towards the surface normal. And these laws, we could also derive them by requiring momentum conservation of photons, and that would be another way of possibility of deriving things. And there the component along the surface would be the conserved quantity. And in a way, this treatment is quite similar to what we do in the follow-up lecture, where we are deriving these by just using the Maxwell's equations and the follow-up boundary conditions that are associated with this kind of given interface between two dielectric media. And now, okay, we could also derive these laws, and I think historically this was the way how things were motivated, was that we could generalize the concept of optical path length, OPL. And here we could just think that the time it takes for light to propagate, and we can write it that the time it takes light to propagate, essentially it's the distance of light propagating in a upper medium with the given velocity, and then it's also the time it takes for the light to propagate in the lower medium for a given distance. And then we could plug values into here. Of course, the speed of light in medium, we can write that as the c divided by n. So we have this kind of equality here, and then we can take c as the common term into the denominator, and we would have this kind of equation for the time it takes for point, or maybe not a point, but the ray of light propagate from point into another point. And now, essentially, we can write an optical path length OPL as the denominator of the given equation. So OPL would be the Ni times Si plus N2 times S2. And more generally, of course, we could generalize things into an integral form, so that the optical path length would be essentially like a sum of small different portions of space where light is propagating. And when we go from the discrete summation into a continuous variable, we would calculate an integral over a line defined with S, so that that would be the proper approach. And now we could apply Fermat's principle, and there the Fermat's principle dictates or states that light takes in the path or traverses the path that is known as a so-called stationary path S. And for the stationary path S, essentially it fills a condition that the partial derivative of OPL as a function of this path length S as a function of ds is essentially 0. So that's why it's called stationary path, so that they essentially, in a way, it's at least a local minima, if not a global minima. And most of the time, this is the shortest path that is the stationary, but it's not exactly always so. I believe that if you would generalize or apply Fermat's principle into behavior of diffraction gratings, you would see yourself that the OPL would have many local minimas, and they would correspond to the different diffraction orders. That's my hunch, at least. Maybe that is the case, maybe it isn't, but at least I recommend that if you're interested in generalizing, go into that kind of problems. So this is what I wanted to say in this lecture. So we have really gone through the basic terminology, what can happen, and we have introduced to you the laws of reflection and refraction. And here, basically, it's the Snell's law that will be used extensively in what follows. And of course, from the kind of point of view of neat physics and what are the concepts that will be useful in the future, optical path length will be highly useful. That will be used quite extensively when we are looking in chapter 7 regarding other things of light propagation, phases and interference effects. And there, this OPL concept will be highly useful. And of course, Fermat's principle, it's a nice thing to know. It's a kind of general principle, and also in a way is connected with this concept of action potential known in quantum physics, especially in the path formalism treatment of quantum mechanics. So I thank you for your time and patience, and please join me soon in the next lecture, where we will be deriving these laws essentially from the Maxwell's equations. So doing a more rigorous approach. So I thank you for your time, and please enjoy the day.